In this demonstration, you'll learn how to set up a steady-state thermal electric conduction simulation to gauge the performance of a thermal electric cooler. I'll start by selecting a simulation process template from the study panel on the left here. I'm going to select the thermal template. I'll choose a thermal and electric conduction simulation and accept the default selection for the options list so that automatic contact detection is performed. In creating my simulation process, the first thing that I'm asked to do is select a geometry. I'll select the geometry file for the thermoelectric cooler. AIM loads the geometry and sets up a simulation process, which will define everything I need to do for a steady-state thermal electric conduction analysis. I'll skip ahead to the loaded geometry. AIM has automatically created the physics solution process, which involves the geometry import, meshing, physics, and results. Here is a summary of all of the tasks, along with their status. My physics solution task, the red exclamation mark here, is telling me that the physics task needs more information before I can complete the simulation. I'll click on it to go into the physics solution data panel. You'll see that a lot of defaults have already been set up for me: material assignments, physics options, contacts, and solver settings. While a material has been assigned automatically to the geometry, I want to change the material to copper for the copper plate and customize it with an additional material property. So I click this default material assignment. I need to make sure I'm selecting bodies rather than faces, so I use the body selection filter. Then I select the copper plates and semiconductor pellet and replace the default location. Now I change the material to copper. Density, specific heat capacity, and thermal conductivity are already defined. I need to add isotropic resistivity by selecting it from the Add Material Data menu. Then I enter the value. I'm done with copper, but I still need to define the material for these two semiconductors. First, I'm going to define the material for this N-type semiconductor. I select it in the geometry. Then right-click to add a new material. I'll name it N-type semiconductor. I need to add my material properties. First, I'll add isotropic resistivity and set the value. I finished defining the material properties by adding isotropic Seebeck coefficient and isotropic thermal conductivity. You can see the values here. I'll now repeat this process and assign material properties for the P-type semiconductor. You can see it defined here. So I have defined 3 material assignments: copper, N-type semiconductor, and P-type semiconductor. I'm now going to add some boundary conditions. First, I'll set a temperature constraint. I change the selection filter to faces and select the bottom faces of the copper strap. Then I right-click to add a temperature constraint and set the temperature. This will allow me to model the thermal electric cooling of this system. Next, I'll ground the end of this P-type semiconductor. I select the end face of this semiconductor and right-click to add a voltage. I'll set this to 0 to indicate it's grounded. I'll also set a current on the input electric terminal and a rate of heat flow to the copper strap. So you can see that I've set up 4 boundary conditions: temperature constraint, voltage, current, and heat flow. Then I'll solve the physics solution task by right-clicking it in the workflow view and selecting Update. The meshing task will also be updated. I can see the progress on the bottom right-hand side here. The update is complete, so now I can view my results. I'll click on the Results task and then Evaluate. I can then expand the Results heading to view the predefined results. The template has already inserted one contour result for temperature. This simulation results in a cold junction. You can see that the face with the heat flux has a temperature close to 0. Next, I can add an electric potential result. On the Results panel, I'll select this Results Add menu, and then select Electric Potential. Then I evaluate the results task again. You can see the current passes from the input terminal to the ground, from higher voltage to lower voltage as expected. This concludes this demonstration of an end-to-end basic steady-state thermal electric conduction simulation in AIM.